Our next speaker is Travis Earles, the Operations Strategy Lead for the Rotary and Mission Systems business of Lockheed Martin, where Travis has previously led and coordinated advanced materials and nanotechnology innovation across the corporation. Before joining Lockheed in 2011, he served as Assistant Director for Nanotechnology in the White House Office of Science and Technology Policy for 4 years. He helped launch nanotechnology research at the National Cancer Institute. Travis?
Thank you, Diane. Thanks to the ACS, and thanks everyone for taking time out of very busy days to be here. I'm very pleased to participate on behalf of our corporation and the kind of stuff that we're doing in this space. I couldn't be more excited about it as well. So I would echo Mike's comments. This is personal for us. We really like this stuff. So I'm hoping that we are able to kind of set the stage for you with these brief statements on the front end, even though they're very compressed, and I know it's a lot of information, and have a really great dialogue during the time that we're here together. So let me just read here a couple things I wanted to make points, and I only have one chart, so I won't be moving it. Lockheed Martin is leading the way in advanced materials and nano development, enabling a broad base of revolutionary capabilities in multifunctional materials and structures, novel sensors and electronics, as well as energy storage. The depth and breadth of our emerging technology initiatives reflect our corporation's commitment to drive foundational innovation and advanced manufacturing as well for affordable global security solutions in aerospace, energy, medicine, computing, and other technology applications. Given the focus of our panel today, I'd like to highlight just a few examples of how we are leveraging advanced materials to lightweight, lower cost, and improve performance on some of our products. I'll start with carbon nanostructures, and Mike set a great table for us there. Combining high performance with the lower cost and ease of manufacturing, Lockheed Martin has developed what's called the Apex platform of advanced composites. It's a versatile materials and manufacturing platform designed to meet exacting demands of defense, aerospace, automotive, industrial, and commercial applications. This platform utilizes a broad range of materials, including discontinuous reinforced molding compounds, continuous woven and unidirectional reinforced composites, and hybrid materials that utilize specialized resins and additive blends. Apex is changing the way that we think about design engineering because it enables faster, less costly, and a smarter way to build high-performance components. Highly automated, variable rate, and energy-efficient thermoplastics and manufacturing technologies, and recyclability, reducing waste and environmental footprints. Lockheed Martin's subsidiary, Applied Nanostructured Solutions, or A&S for short, has created a process to infuse multi-walled carbon nanotubes with glass, carbon, and ceramic fibers in a continuous high-volume production process. These infused carbon nanostructures are also versatile platforms for users to create the next generation of low-cost composite materials with enhanced capabilities, electrical, thermal conductivity, advanced shielding for electromagnetic interference protection, protection against lightning strikes. So we have a couple of examples where we've actually transitioned some of this material, and the images on the upper right start there. At sea, Lockheed has developed a potential replacement for the cumbersome jack and ensign staff, which is the staff immediately in front of the individual at the front prow of the ship. These are being replaced with lightweight carbon nanostructure infused composites that simplify installation and operation of the staffs, both fore and aft, improving safety and reducing the crew required from the task from 3 down to 1. Similar transitions are in process to create lightweight structures for the main mast, as well as other parts of the ships and the Navy needing lightning strike protection. So we not only are able to succeed in weight reduction, but we're adding some functionality in the material as well. In space, the inset in the middle is a picture of the Juno satellite, which is currently circling Jupiter. We were very pleased to produce the carbon nanostructure infused fiber used to make contoured supports on that satellite to help prevent thermal blanketing from interfering with Juno's solar array support mechanisms. Our team took that idea and deployed that next generation material in just 4 years. This technology is being applied not just to structural materials, which I primarily highlighted structural examples here, but I did want to just point out, and I was pleased to see that Mike noted, applications in things like cables and wiring and shielding. Makes a significant difference if we're able to make just a small percentage dent in weight saved there. the performance, improving the efficiency of the conductivity, or improving the shielding, taking the weight out of the existing copper cladding. All very, very helpful. But I also wanted to note a couple other areas where we're using our carbon nanotube technologies. They're forming the basis for novel electronics and sensors as well that offer scalable and tailorable sensor platform solutions, high sensitivity, quick response, selective target discrimination for multiple analytes. That's functionalized and unfunctionalized. So what that means is basically a bare carbon nanotube. We can use that as a sensor directly, or we can also functionalize it with, coat it with some materials to also function as a sensor. I didn't put up an image of it here, but we're also looking at using those CNT-based sensors to reduce weight on our Orion human space platform, the Environmental Command Life Support System. For that is currently 4 major bulky sensor modules, and we're looking to replace it with that chip right there. Lockheed Martin's research teams are also creating more efficient, environmentally sustainable, and cost-effective silicon and carbon-based novel energy storage solutions. We've designed nano-infused electrodes that can tolerate much higher loadings of lithium, in addition to batteries that retain their performance characteristics over a wider range of operational temperatures with newly designed and improved electrodes. Test results on the electrodes and batteries built with nanosilicon anodes already show superior performance. I wanted to highlight a little bit of our work in advanced composites, and there are many examples that I could draw from, but being that we acquired Sikorsky last year, I wanted to highlight some of the work going on there. Sikorsky has designed and built the CH-53K heavy lift helicopter to carry more than 27,000 pounds over a mission radius of 110 nautical miles, which is more than triple the external load carrying capacity of its predecessor, the CH-53E. With a similar footprint, the 88,000-pound maximum gross weight kilo aircraft features powerful new engines, lightweight composite structures, an innovative transmission design, and 4th-generation main rotor blades, which are also very advanced composite construction, as well as fly-by-wire flight controls. This heavy lifter will allow the U.S. Marine Corps and other international militaries to move troops and equipment from ship to shore and to higher altitude terrain more quickly and effectively than before. So as you can imagine, being a heavy lift helicopter, every pound of weight matters. And so the majority of the CH-53K heavy lift, the replacement intended for the CH-53E, the fundamental large composite structures are key to achieving the performance that the Marine Corps requires for that bird. Lightweighting benefits its mission effectiveness, its affordability, and its producibility. The composites enhance load-carrying strength and producibility most in large planar parts, such as the highly loaded cabin skins and the moderate to lightly loaded internal structure of the aft cabin. The technical fellow at Sikorsky, Daryl Toney, has noted that the main rotor attachment to the fuselage, where all those lift and control loads come into the fuselage, is supported directly by titanium, but once you go forward or aft, all of those loads are supported by advanced composite beams. So the composite structures, while in general 20% lighter, this is a general rule of thumb, 20% lighter than metal as a general rule. With the CH-53K, Sikorsky engineers reinvested some of the weight savings for ballistic protection. So we also, I didn't mention on the Navy transitions, whenever we're able to reduce weight, we actually could enable further capability because of that. So it may not just be a flat-out reduction in weight, it actually may be the addition of electronics or sensing capabilities as well. So these are just a few of the examples of our advanced materials, and for lightweighting at Lockheed Martin as well as other areas. I just wanted to note in closing a couple of the areas that I feel would help us is a rising tide would lift all the boats. It's not just specific to Lockheed Martin. It's not just specific to the aerospace and defense industry with respect to advancing materials and manufacturing writ large. And those are just listed here. The challenge of qualifying and certifying new materials is enormous, extremely expensive. The majority of the way we move a new material into commerce today can be anywhere between an 8 to 12 to 20-year time frame, requiring multiple millions of dollars to prove that a material is capable and can do what the makers or the users say it can do. Huge, huge challenge. Diane mentioned at the beginning how ACS has played a central role in forming databases. The materials data infrastructure, having a way to track, even internally, let alone across industries and across sectors, who's using what material and what are the properties associated with that material would be a huge benefit for, all, again, rising tide lifting all boats for across the board. So I'm hopeful these are a couple of areas we'll have a chance to talk about more later. Thank you very much.